Welcome to the CS210 video on assembly programming. So to start, we're going to have to download the assembler, and you can find that in your files and the assembler.asm.zip file. You could just go ahead and download that and unzip it onto your desktop or another place where you know it will be located. Next, open up a command prompt, change directories into your assembler directory where you just downloaded that file and uncompressed it. And then to launch the assembler, you do Java TSC assembler. And notice the TSC and the A are capitalized. And that'll launch up your assembler. Now the assembler is just an editor that allows you to type in your assembly programs, and then it assembles them into ones and zeros. And it will save a file that you can use your loader that you did in the last lab to load into memory. So to go ahead and get started, you need to create a new file, and it asks you where you want to save it, and I'll just save mine on the desktop. And I will call this my first .tsc. So you have to save it with a .tsc extension, or else it won't work with this assembler. It's pretty picky about the extension. So go ahead and save it there. And now we have a window that we could type into. And just so you know, a semicolon is a way that you can do comments. It's only a one-line comment, so we can put any comments we want after a semicolon. And I'll use that throughout this video. Now next, we need to open up the programmer's reference, and you can find a link to that probably in your labs or also click on the online textbook, but you can click on the instructions and get to this TSC programmer's reference that lists out all of the instructions we have available. Now, hopefully from your reading, you also know that other things that you might type in that are not instructions are assembler directives. And we'll specifically be using the .org and the .end in this video. And other assignments will require you that you use the BSC and the BSS directives as well. Now, the difference between writing a regular program and a program in assembly is, first of all, you're going to need a lot more instructions to do simple tasks. And second, we have to worry about our memory and our registers. So we need to keep track of those somehow. Now, first of all, we need to decide where we want our program to be loaded in memory. So I'll usually tab over a couple of times, and you'll see why I put this tab in there later. It's not required, but it will help you later on. And we do a .org, and this tells us where we want the instructions, whatever comes after, to be located in memory. And in this program, I want to put it in the very first memory location. So you could put this number in any format, but this says it's a hex number, and I'm going to put it in memory location 0000. All right, now what about keeping track of our registers? So usually maybe on a piece of paper you might want to do this, or you can put this in the comments. We'll have our 4 general purpose registers. So we have our registers, and what the information we want to know is we want to know the current value that might be stored in that register. So if we put a number inside of that register, we might want to know what that number is. We also want to know what the purpose of that register is. Now, again, this is notes that you could scribble on a piece of paper, or for the video, to make it easy for you to see both my notes and the program at the same time, I'm just putting these in comments. Now, one assembler directive required in every program is the .end, and that just marks the end of our assembly program. Now, even if you have a .end, you can't put gibberish behind it. You need to either comment out any comments, and you can't put stuff that isn't valid assembly outside of the .org and .end, but we do need the .org and the .end. Now, let's get started writing our program. Well, what program do we want to write? Probably something pretty simple and easy for our first program, and we'll just do a loop that adds up all the numbers from 1 to 100. So to do that, what I'm going to do is I'm going to write this program in Python, not perfect Python, but either Python or a pseudocode, some language that you know. So we want our sum to equal 0. And then we want to go for each number in our range from 1, because we want to add up from 1 to 100. So I need to go to 101 to end. Now, if you remember in Python, it doesn't do the last one. And then inside of here, I just want to do sum equals sum plus the number. Okay, so now I have a little Python program. Of course, this isn't valid assembly, so I'm going to put some semicolons in front of it for some comments. Okay, and so now we have at least some pseudocode or something to help guide us. So in your assignments, you might be given this, and that's really nice. You might be given some code and say, hey, turn this into assembly. Another thing is they might give you something that you need to accomplish. And if you can't write that in a regular programming language, you're going to have a really hard time writing it in assembly. So step one is to always come up with some code. It could be a pseudocode, it could be Java code, or anything that accomplishes the task you're trying to accomplish. And then after we've done that, what we want to do next is look at our variables and decide where they're going to go. Luckily, we only have two variables. We have sum and num. And so we have 4 general purpose registers, so we don't have to worry about moving the variables from a register and storing them in memory. We have enough registers that we can do that. So maybe in the purpose, in register 0, I'll put sum, and in register 1, I'll put num. That gives us 2 extra registers just in case we need them. And we're just kind of mapping out where our data is going to go. Now, this is a step that you do not have to do when you program in a higher level programming language because it handles all of that for you. But when you're programming in assembly, you have to keep track of what you're going to do with your registers and what you're going to do with your memory. And the next step is to read through all of these instructions and get a general idea of what they do. Now, the instructions that are really important that you're going to need to know are the adds, add and add immediate, all the branching instructions, so branch greater, not branch on equal, branch greater than 0, branch less than 0, branch on not equal. We'll definitely use the halt, which is a pretty easy instruction. It just stops the computer. We have jump and link. We probably won't use that much in the class, but the jump we will use. The jump register and link we won't use too much. Then we have the load address, which you'll need to get familiar with. We'll use that quite a bit. The load word and store word are how we interact with memory. Of course, we have some other mathematical operations like subtract, two's complement, shift left, and shift right. Now your input output is handled by the read word and the write word. So make sure you read through these instructions, get just a general idea of what they do or what you can accomplish with them. And now that you kind of are hopefully somewhat familiar with those instructions, we could go ahead and try to convert this code into assembly code. So step one, we need to make sum equal to 0. So sum is going to be stored in register 0. So I want to do is put a value of 0 inside of there. So how can I do that? Well, the one instruction that allows you to load a number into a register is the load address instruction. And then we need to say what register. So I wanted to say register 0 and then the value. Put 0 into register 0. All right. Next, we need to work on this for loop. Now the for loop might be kind of hard to handle, but so maybe we'll save that for last and we'll move on to this instruction right here. What we want to do is we want to add the sum and the number and store the result in sum. So what we want to do is add register 1 that has our number, hopefully, and register 0, which has our sum in it. Now, I said hopefully because we haven't done anything to put that number into register 1 yet, but that's our plan. So what we want to do is add these two registers and store the result into register 0. So in that instruction, to add two registers together is the add instruction. And then the first argument is where the result goes, and the next two are the two inputs. So this says add register 0 to register 1 and put the result back into register 0. So that has accomplished this step right here. Next, we need to worry about this loop. Now, a loop accomplishes a lot of tasks with one line of code. First of all, it initializes our num variable to 1 to start. Second, it increments num every time through the loop, so it's 2, 3, 4, 5 in each time we go through the loop. And then third, it also has a ending position, and it makes the code inside of it get repeated. So we're going to have to take this for loop and the things it accomplishes, initialization, ending point, and the actual loop itself, and we're going to have to break those down into separate assembly instructions. So if we look at the for loop again, what it's going to do is it's going to initialize number equal to 1. Then it's going to repeat. This is the meat of the loop, or what it repeats each time. At the end of the loop, it needs to add 1 to num. And then if number is less than 101, then it needs to repeat the loop and come back up to here. So we kind of have this loop going on through here. So this high-level for loop in Python does a lot of work, and we got to separate out that work. So first, let's go ahead and try to turn our number and set our number equal to 1. And the easiest way to do that is with a load address again, and we'll set the register 1, which stores our number, to 1. Now I want you to pay attention here. If you notice, there are dollar signs in front of registers, but in front of hard-coded numbers like 0 and 1, we didn't put a dollar sign in front of that. Now we'll get rid of some of these notes here, but I'll still leave a little note behind each line or comment saying what that line does. So now we need to add 1 to our number. So we can do that with an add immediate, and that's $1, $1, and 1. So if you look at the programmer's reference, this is the destination register, this is the source register, and this is the immediate value. So take the hard-coded number 1, add it to whatever's in register 1, and store the result back into register 1. Finally, we need to repeat if the number is less than 101. So we need to do a comparison here. And now let's look at our instructions to find out which instruction we can use to do that comparison. Now, these are our branching instructions that we can use to make loops and if statements. What they do is, under a certain condition, if the condition turns out to be true, then they cause the PC counter to jump to a different spot so that we can create loops and if statements. So we can use this branch less than 0 right here. And if a number is less than 0, then it will make the branch. But that's not going to work for us. We can do branch greater than 0. So if a number is greater than 0, then it will branch for us, but that won't work. We need to compare 101 to whatever num is in. And the only way to compare is branch on equal or branch on not equal. And I think we want to use the branch on not equal. If 101, if our number is not equal to 101, we want to go back and do the loop again. So if our number is not equal to 101, then go back and do the loop again. And so this right here is the middle of our loop. So I'll just indent that a little bit so we can see the loop. And then if you notice, I have this add 1 to number inside of that loop. So we could say branch not equal, and we just have the two registers. So register 1 is our number, but we need to compare it to 101, and this won't work right here. We can't hard code a number. And then where do we want to go back to? We want to go back to the start of the loop. So I'm just going to say loop there. Now here is the beginning of our loop. So we can actually connect that up just by having the labels be equal. If you noticed when you translated the loader lab, you use these labels as well. So labels mark a memory location where an instruction might be, and you can use the labels. That way, if we add more instructions in here, the assembler will go ahead and connect up the branch to jump back up to this instruction, no matter where it is, as long as these things are spelled the same. So that's really nice that the assembler will do the figuring out of that. Back to the loader lab, remember you had to figure out where you want to move the PC counter yourself. This will do it automatically. And then afterwards, let's go ahead and print out our sum. So that's the right word. And it will print out our sum. So that's register 0, and then we'll halt. And I think we might have this done all except for this part right here. We need to compare to 101, but branch not equal only compares two registers. So I need to get 101 into a register. I will use register 2 here. We want 101 to go in here, and I'm just going to say stop point as the purpose. So this is when the loop should stop. To do that, I'll go use my load address, and in register 2, I'll put the number 101. Okay, and notice how this little chart kind of helps, or this writing this down or putting it in comments somewhere helps me keep straight what register is what and what value I put in it. And notice that does not have to be part of the loop. We could put it in the loop, but it's kind of pointless. We just need to set it once and then keep going. So now we have all of this in our loop in our program. We have the .org, we have our .end, and we have this loop with these two things getting repeated over and over. And notice we're adding 1 to number each time, so we're eventually going to finish. Now all we need to do is say use register 2, that is our stop point. And when we're done, we can go ahead and save it by clicking that. Then this button right here is to assemble it. And we'll go ahead and assemble and press that button. And if everything works out correctly, you should see first pass, second pass, and then creating the name of your file .bin. This is a binary file that you can load into memory using your loader. Also, if you look at your desktop, you'll see that .bin file. Now, one thing to know, if you have a syntax error, let's say I put an extra comma somewhere, and I try to save this and assemble it, notice it says one error found, okay? If that happens, this assembler isn't nice. Your first .bin file is still there from the previous time, but now you have an error and it's not changing. So really, every time after you assemble it, make sure you have that success, so you see the success. So go ahead and assemble that. And we got that there. And now all we need to do is run it. So to run it, we're going to launch up our TSC simulator. We're going up to the File menu, and we're going to load our loader that we did in the last lab from a ROM. So go ahead and select that. So I'm selecting the loader.rom, and we're going to go ahead and open that. You can go ahead and scroll down and make sure your loader's in memory. And as you can see, my loader's there. Of course, it's grayed out just so you can't cheat on the loader lab. And then we go ahead and say File, select our input file, and be careful and make sure you select the first .bin file, not your first .tsc file. Okay, once we have that, notice our input source is the file, and we have our loader loaded in. We go ahead and do FFF5. Click Load PC, and I'm going to click Start. Now this is running the loader, not your program, and it put my program into memory. Now I can clear my registers, just to make sure they're clear. You don't really need to do that, but the one thing you want to do is make sure your PC counter is now pointing at the beginning of your program. And then we'll go ahead and clear our trace just so we can see that. And let's go ahead and do a step through this kind of slowly at first, and then we'll click start and go fast. So now LHI, I didn't use a LHI instruction. Where's that from? And then the or immediate too. I didn't do those instructions. Why are those two instructions there? Well, that's the load address. Remember, the load address is that pseudo instruction. It takes two instructions to put an entire number in a register. But sure enough, we have the number 0 in register 0. Let's go ahead and step two more times. Now put 1 in register 1. And then we'll step two more times. And now we got, it says hex 65, but my guess is that's 101. And if we want, we can register 2 to assign decimal. And sure enough, we have 101 in register 3. Now we can step again. We're going to add register 1 to register 0. And we're going to get 1, and then that result went there. So that's register 0 that was 0 plus register 1 that was 1. And our answer is 1, and it gets put back into 0. We can step again, and now our num is now equal to 2. Now let's step again. We have branch on not equal, so it's checking register 1 and register 2, and since they're not equal, it subtracted 3 from our program counter, so our program counter moved back up to the add instruction. So when we step again, now we add 2 plus 1 and get 3. And then step again, and now we got 3 in register 1. And now our branch and not equal moves the program counter back up to the loop. And now we'll just click start and let this finish. And we finally got our final result in register 0. And here is the binary version of that. And we can acknowledge our data, and then we halted. Now, if we really want to see what that final answer is, we can go to register 0, see sign decimal, and that is the sum of all numbers from 1 to 100. So that's the right answer. Our program did what we wanted it to do. So there's an introduction on how to write an assembly program. After you assemble it, we use the loader to load it into memory, and then we can either step through it or we can run it fast. If our program isn't doing what we want it to do, then we can use this debug console and try to figure out why it's not doing what we wanted it to do. Thanks for watching.